Speaking of reliability, a podcast with good friends talking with you about reliability engineering topics. Welcome to Speaking of Reliability. This is Fred Schenkelberg.
This is Enrico Belmonte.
Hey, Enrico. I think this is a record for over 1,000 episodes, going from, hey, how you doing, Enrico?
Really?
Good talking to you, to hit record. Because I know you've got time constraints and family things you need to attend to and stuff like that, so I respect that. But you mentioned reliability allocation as a topic today. What do you have in your mind with that?
I want to challenge you a little bit with
Okay.
this topic, Fred, because at the end, with reliability allocation, it turns out that you need some numbers to allocate.
Yeah, you do.
And basically, what is reliability allocation for people that are listening to us? So generally, you set a reliability target at system level, and you break down it up to subsystem level, component level, design element level. And it turns out that the more the component, the more the layer you have, the more challenging, let's say, the reliability target will be. So if you start with 90% for a product, it turns out you will end with, like, I don't know, 1,000 ppm for a design element. So for a screw, for whatever. Okay.
It's a good explanation. I did run into an organization once that had a 50% field failure rate. Half their products they shipped came back within a year. And
in the first year, 50%.
Yeah. And they've been doing it for years like that too. And they had a 95% system reliability goal for 1 year, for example. And they had 5 main subsystems. And when I went and talked to the design team about, what's their goal, and how did they source the components? It was like compressors and pumps and stuff like that. They said, well, we looked for ones that would meet the 95% reliability for the component. And they said, yes. And I said, well, let's do a little bit of quick math here. And if you multiply 0.95 to the 5th power, you get about 50%. And I said, you guys, I don't remember the exact numbers and stuff, but the rough calculation of using the system goal for each component almost identically matched, within like 1%, what their field failure rate was. And so I was impressed that the designers could find and design elements of their system that actually hit a target that well across all their systems. Unfortunately, they didn't have the concept of apportionment in place. They all assumed that if they made 95%, everything else would be perfect. And that doesn't work that way.
Yeah. No, I agree. I think this is the first message that I want to. My first takeout message is that we need system reliability engineer, right? So system reliability engineer is person who is deriving the target, or is contributing to derivation of the reliability target with the management. Because at the end is the business decision. We talked about that a lot of times. So if you design a product with a reliability target of 90% in 10 years, it will look different from a product having like 50% reliability in 10 years. That's no question
definitely.
about it. And that is one part. So this is about, derivation of the reliability target at product level. The allocation, the apportionment, as you said, is about how to break down it. There are a lot of different approaches. There are, for example, the ARINC, the agree, the equal distribution of reliability. I think it's a good tool for this allocation for monitoring if different design teams are doing job properly. If they don't, let's say, if they don't follow two different goals, so you have, for example, five subsystem. Subsystem A is great. They are working hard for getting higher reliability. Subsystem B, the reliability is really poor. If they are in series, the example that you just made, is showing that the weakest link is that the link that is failing, of course, first, and therefore is determining also the reliability of the system.
Yeah.
And I just want to conclude saying that if you have a good allocation, you can negotiate between different teams what is the requirement they can accept.
Mm-hmm.
And that's, I think, is a good strategy for achieving a good reliability target at the end.
I'm glad you mentioned that, because I mean, I want to come back to the reliability tools and various methods to achieve it. I think that's important, and to what level you do it. But the primary benefit I've ever seen with apportionment is that it gives the various subparts. If, let's say you're working on a device like the one I mentioned earlier, it has a compressor, it has a pump, it has a power supply, other dominant subsystems, and there's a team like electrical engineers are working on the power supply, mechanical or the folks that deal with moving fluids around, I forget what their name is, they're working on the compressor or the pump, and they may or may not talk to each other except maybe at a team meeting, where the whole program gets together. And the absolute best value I've ever seen in an organization was working on a workstation, and they actively negotiated in every meeting, and it was a series system. So the program manager would look at, I'll pick on power supply, because that week the power supply's reliability was the weakest link, and we'd look at them and say, all right, Sarah, you need to, what are the options to improve the reliability? What is technically feasible, budget feasibility? Give the team some options. How much better can you get? And at what cost? And then they'd come back with a proposal of a couple of options. And then they would say, well, that's too expensive to get to the full goal, but all right, keyboard folks, do you need all of the apportionment that you have? And they like, no, not really. We have margin there. And they would give up a little bit so that the math would work out. But what it did is that it focused on the area that needed an improvement. It gave them a flexibility. It's not a hard and fast rule. I don't think apportionment should ever be a hard and fast rule. It should always be a give and take. Where are you going to allocate resources to improve reliability in a meaningful way? And if it's part of the weekly discussion of the team that's allocating engineering talent and resources and funding and everything else, that's the optimal for me, is where it really, really should be.
I agree with you. So negotiation, I would say, is the topic number 2 after system engineering. You need someone coordinating, also moderating this negotiation phase.
Ideally, that's your program manager or whoever's in charge of the project. Yeah. I want to come back to before we get too deep into this, is that there are technical tools out there and mathematical algorithms, and some you need some estimates of different levels of reliability already, and some use cost features in it and so on. I have found all of those to be not really useful. They'll give you good numbers. I don't doubt that. But I found that if you go into that program meeting and say, all right, we have 5 teams working on this for your area, say power supply, how reliable can you get a power supply that fits our budget? And they come up with a number. And it's at that point, it's probably just a guess. Right? And you say, all right, we write down 0.98. And then what's yours? And then we put them all down and say, all right, we're 3% below our system target if everybody meets their objective, right? You're the weakest link. Go do some research. Go figure it out. And because what I find when you use say a system engineer goes off and uses a calculator of some sort to come up with goals, the rest of the team goes, oh, that's the goal. And either I ignore it because it's not realistic or whatever. And what I find is to start the negotiating or the give and take kind of discussions requires the buy-in right at the start. And so I skip the fancy reliability stuff, engineering tools that we have available, and say, all right, mechanical team, electrical team, software team, what can you do? What do you commit that you can achieve? And you can use field history, you can use, whatever basis you want to come up with that. But the first discussion is really more about starting the ongoing discussion to adjust those reliability portion goals throughout the program to meet the system goal. Because the alternative is I find that the teams mostly just ignore the apportionment if they're not involved in setting it.
Yeah, I think that's a good message. It's not just a matter of setting or locating some numbers, but it's about negotiating what is the limit, the design limit design team can achieve
Mm-hmm. And
in order
budget too.
yeah,
And budget.
in order of course you have different boundary conditions, right?
Mm-hmm,
Cost
mm-hmm.
and reliability is one of them.
Yeah.
But if the cost generally is well tracked,
Yep.
reliability is in the organization that are not so mature is not tracked. So there is the risk that every design team is developing its own subsystem and then try to integrate it somehow without considering what is the impact of
Yeah.
different reliability approaches.
Yeah.
That's pretty risky. Yeah.
Yeah. And I agree. That's very, very risky. Now, one other thing you brought up I want to circle back to is this: what level do you go to? To component or design feature and stuff like that. And I imagine that I'll use an inkjet printer, for example, because I'm familiar with them. I think at one point I understood there was close to like 600 or more. I think there's more than that. It's just 600 components on the circuit boards. And then I'm sure they're doing better now. The mechanical system was probably close to 1,000 or so components, if you count every discrete, item that gets assembled into this thing. And inkjet printers are not the most complicated thing in the world. Can you imagine how many components go into say a battleship or something like that when you count all the parts in every communication device and weapon system and everything else? My advice to most teams I worked with is do the apportionment to the level where somebody has to make a decision. And it's usually at like the mechanical engineering team might have, 5 or 10 people working on the program, but that engineering manager is the one managing that subsystem, say the mechanical device and a printer. And they're responsible to go back to the system team to say, hey, we're on target for our goal or not. And then they may discuss, it's this one gear assembly that's a problem, and then they tie into it. But I find that going to, individual gears or individual parts, like major elements of a circuit board or diving too deep into it is confusing to most of the engineering team. So I reserve it to, all right, mechanical guy, why can't you meet your goal? Well, it's this gearbox assembly here. Well, how good can you get that part versus the other components in your overall system? Maybe we can do some bartering or trading of this allocation within your subsystem, as opposed to imposing that right from the start. Because I found it to be a minimal. I see it more as a distraction when it gets too detailed.
Mm-hmm. I agree with you. I think the point that you mentioned go so deep, so at the level where you have to take the decision. Yeah.
Yeah.
And in many cases for mechanical engineers at component level.
Yeah.
So in case of the gearbox, for example, it could be a gear wheel, and then you need to validate or to verify that you can reach reliability that
Yeah.
you will be assigned to. Yeah.
But then you would do the apportionment at that time to say, well, how reliable does this gear need to be? it's, I mean, we still need to get down to details. If let's say that gearbox has 8 failure mechanisms due to different elements of the system, well, then you need to apportion it to those failure mechanisms, the dominant pieces, and they're usually associated with different elements of the system, design elements. I get that. Yet if the gearbox is never an issue, it's fine. We have plenty of evidence that it's going to meet our reliability target, not cause a problem on the overall mechanical system. Then we don't really need to do the apportionment for those elements. So I think it's a delicate dance there to keep an eye on.
It's a trade-off.
Yeah. But there's, I mean, I've seen, and Carl tells the story where the reliability team that he first started working with and managing, they would do a reliability apportionment to every component in an automobile. So, and every component. And they would write this great big huge document that listed all the expected components and all the systems they had. And then but they only could do it once they knew what most of the bill of material was, right? So everything would be 95% designed, and they have this big bill of material, and then they would sit down and do the apportionment and send a memo out to the team saying, all right, here's the apportionment. Here's how reliable all these components need to be. The design was done. It was too late and not useful, and it didn't help them make any decisions, and they mostly just ignored
probably for the next generation, probably, I don't know.
Well, maybe, and I think it might have been used for sparing, or it might have been used, but what Carl talks about, and what I found myself, is that for sparing or for repair systems or stuff like that, people kind of use historical knowledge or their own experience. I haven't met a motor sergeant yet that, a shop that says, oh, I use the apportion numbers and the FMEA to set up my stock for spares. No, I've been doing this for 10 years, and this is the kind of stuff I typically need to have on hand. They just know, it's not technical in any way, but they're still in business. Yeah, they could streamline it some, they could do some other things with that, but the apportionment to me is primarily a wonderful tool to have a discussion in your team to do 2 things. One is keep the awareness of paying attention to reliability in the team. So you talk about it on a regular basis, and you have this target that you can talk about and then adjust as needed. And then 2 is to avoid everybody designing to the reliability they think it should be. Because if you over design if somebody thinks it needs to be super reliable and it really doesn't, well, we're wasting energy resources on that element. And so and vice versa. If somebody, I talked to a team, and these 2 engineers were working on the exact same circuit board. They were working on different elements, different factors or features within that board. And one was gold plating everything, buying the most expensive components because she believed that it was going to be very difficult to meet the reliability goal. And she happened to be right. The other one was, oh, this is easy. This is, easy peasy stuff. I'll buy the cheapest components and doing all that stuff. And of course, it was the engineers' elements that were designed into this board were the ones that were causing them all these field problems, because he just didn't understand that, if I don't design it to meet minimum amount to make the system work, it's going to cause a problem. And so it's
and then you start again from the topic value. Now, what is the value that we can generate by doing reliability? And if we don't do reliability, what is the consequence that we expect? There's another point I would like to mention or discuss with you before closing this this podcast. It turns out that when you apply reliability allocation, it turns out that at component level you might have like 1,000 or 500 or 2,000 ppm, so part per million.
Or even smaller.
How do you deal with this? How do you deal with this difference? In your experience, what do this difference? How can this difference be considered? Like 500 ppm difference?
It's. I mean, there's there's always a level of uncertainty around what is the actual reliability going to be. Now, if it's a critical element and we really need to know and reduce the, you know, I always talk about estimating reliability, whether it's for the system or a component level, is a spectrum. We can just do engineering judgment, which is like an
Yeah.
educated guess. And if it's the range of expected values among our various experts that look at this thing, people familiar with this material or properties or history or whatever, if they're all order of magnitude better than what we need, I'm good with that. Just use it. Just
Yeah.
pick a number out of that range and go with it. Now, if it's a brand new critical component, it's a brand new technology our team doesn't have experience with, it's the first time we're manufacturing it, stuff like that. Those are the signals then, oh, we better, take a look at maybe doing an accelerated life test or doing some simulation so that we can
Yeah.
understand the failure mechanisms, do the FMEA on that element, that component. Do halt. Well, how does it fail? Those kinds of things gets a lot more attention. And all of those tools help us reduce the variability of our eventual estimate of it.
But yeah, if you have some assumption and it turns out that you have exceeded the reliability target by 500 ppm.
Mm-hmm.
So instead of having, let's say, the target is 1000 ppm and you have like 1500 ppm, are you going to optimize to optimize the component
No,
despite the all the assumption that you have done in order to get to this number?
no. At that level, when we're in hundreds of
Yeah.
ppms and in
Yeah.
electronics, especially, it's like no, because if I go to like a capacitor that's a 0204 and I can get another capacitor that has a little less reliability, but it costs a little less, it's not worth the energy to make the change. I
Yeah, I
mean, there is
agree
a
with you.
cost to do stuff like that. Now, stuff in the thousands of ppm, you know, you got to pay attention to the price points and size differential because changing a component almost never is free. Just the logistics of it. If we have
Yeah.
existing stock and preferred vendors and we already use this particular screw or gearbox or whatever, it's often much more economical and safer to use the one that's a little bit better than it should be or a little bit less reliable than it should be versus spending the thousands of dollars to redesign the system around the new component.
Yeah.
So you get, if you just optimize reliability, there's no trade-off. We'll go to the most reliable all the time. Yet that's not in the best service of the system or our customer.
Mm. I think that there is the gray area, no? So where the engineers together need to make a judgment. Okay,
Yeah.
what about this 500 ppm more than expected? Yeah, because 500 ppm, if you sell like 1 million, yeah, is like 500
Oh
500
yeah.
parts
Yeah.
more than fail. If it's safety critical, okay, if safety critical is a different story. I wouldn't agree with what I said. So
Yep.
if it's
Yep.
safety
Yeah.
critical, you need to prove that you are below 1 ppm. But there are
Yeah.
some other important issues that might be impacted by 500 ppm. What I'm
Yeah.
trying to say is that you have, in order to get to this number, you have made a lot of assumptions before
Yeah. Yeah.
that might impact much more the calculation than you expect. So I think that is where the engineers should, yeah, discuss together and make a good decision.
Yeah.
Yeah.
No, totally agree. And I think it's more about that we have those discussions, and there's examples if getting the more reliable component is free, essentially, you're at the point in the design where I can choose this one or that one. There's no real price difference, and it's in
Yeah.
ours. We have the component. Yeah, obviously, just use it. If the other part is if it is a component that I have to make a decision, but it's going to require $500,000 of research to know that it's
Yeah.
working or not. No, I'm not going to go that way.
Yeah, it's a
Uh,
good trade-off. Yeah, it's a good
there's
trade-off.
always a trade-off. I think what's most important is I think what the most valuable part of apportionment is it gets the team to think about reliability and it puts it in
Yeah.
context for the area, the subsystem or component that they're working on. I think that is more important. The actual calculation and so on, if it's a 500 ppm difference, yet in the big scheme of thing, it's orders of magnitude away from the things that are going to cause the overall system to fail. It's a lot lower priority than the one that's going to cause the 8,000 ppm problems. Let's focus our energy on solving that one first.
So we have touched different topics, Fred. We have touched the topic reliability targets, system engineering, allocation as negotiation, let's say, and finally, how to deal with real numbers. I would love if people listening to our podcast would add something that we are missing about this important topic.
Yeah, and that includes, where you didn't get it quite right, as I talked about that one organization that used system reliability for all of their apportioned components or all their subsystems, or a good success story where it really works for you. And, how much does the culture work for you, or how much does the technology approaches work for you? Let us know. Head over to accendoreliability.com/go/SOR. There's a couple of ways to get in touch with us. Enrico and I and the other hosts are available through LinkedIn and our About pages. So as Enrico said, we'd love to hear from you, and I certainly agree with that. And we've been getting a good number of questions lately, Enrico. So next time we talk, we'll have to dive into one of those.
Okay, great.
All right. Well, thanks so much, Enrico, and good topic.
Thank you for the opportunity. Yeah, talk to you soon. Bye.
Talk to you later. Bye-bye. Thanks for listening to Speaking of Reliability. We invite you to join the conversation. If you have a question or a topic that you think we should discuss in a future show, please let us know. You can find a comment box below the episode show notes, or just leave a note as part of a review on iTunes.